When you hear these two notes played back to back, your ear recognizes that they sound like the exact same pitch, just at a different register. Musicians call this relationship an octave, but that auditory connection is actually dictated by a strict mechanical rule in the physical world. Take a look at A4 and A5 on a standard keyboard. Every physical key corresponds to a specific vibration speed. A4 vibrates exactly 440 times per second. By the time we travel up and hit A5, that frequency reaches 880 vibrations per second. This chart shows how those two vibrations interact. Frequency is measured in hertz, meaning cycles per second. Look at the solid blue line representing A4 and the dashed red line for A5. In the time A4 completes 2 full wave cycles, A5 completes exactly 4. Moving up an octave requires us to double the physical frequency. The musical shift you hear is the auditory result of a precise 2-to-1 mathematical ratio. If we count the physical keys from A4 to A5, including both endpoints, we get 13. But to figure out how to divide the octave evenly, we have to count the spaces between them. We are actually measuring exactly 12 steps, which musicians call semitones. You might try dividing the octave linearly. The difference between A5 and A4 is 440 hertz. Divide that by 12, and you try adding exactly 36.6 hertz for each step. That system fails completely for human hearing. Because our pitch perception processes geometric growth, we have to use a constant multiplier, a ratio we can call R, instead of adding a fixed number. We can write this geometric growth as a single algebraic equation. Start at 440 hertz, multiply by our unknown ratio R exactly 12 times, and we must land exactly at 880 hertz. Divide both sides by 440, and we get R to the 12th power equals 2. To isolate R, we take the 12th root of 2, which gives us approximately 1.059. Every time you move one key to the right on a piano, the frequency increases by about 5.9%. Now that we have our ratio, we can find the exact frequency of any note on the keyboard. Using this exponential formula, take a moment, pause the video, and try to calculate the frequency exactly 7 steps above A4. Here is how that math works out. You take the starting frequency of 440 and multiply it by 2 to the power of 7/12. That gives you a frequency of 659.26 hertz. This specific irrational number, the 12th root of 2, is the mathematical engine for modern tuning. It allows musicians to play perfectly spaced steps across any key on modern instruments. Multiplying by a messy decimal like 1.059 gives us perfectly tuned frequencies, but it is a terrible system for human brains trying to measure distance. We naturally prefer additive steps. We want a ruler with equal markings. To translate multiplicative ratios into additive distances, we use logarithms. A logarithm takes a complex multiplying factor, and by funneling it through a specific function, outputs a simple additive number. Musicians use a logarithmic ruler measured in cents. The formula for calculating cents requires 2 variables, f2, your target frequency, divided by f1, your starting frequency. We already know that an octave has a strict 2-to-1 ratio. If we replace the f2 over f1 ratio with 2, we get log base 2 of 2, which is just 1. Multiply that by 1200, and our octave equals exactly 1200 cents. The cent system allows musicians to completely ignore the complex exponential curve of pitch. Instead, they can communicate using an easy, flat language of 1200 equal points between an octave. Let's test this system to see if it maps perfectly back to our keyboard. We can plug our derived 1 semitone ratio, the 12th root of 2, directly into the cents formula. By the standard rules of logarithms, we can take that exponent, 1 over 12, and pull it out of the logarithm, moving it to the front of the equation as a simple multiplier. What we have left is 1200 multiplied by 1/12. The math simplifies perfectly to give us exactly 100 cents. We now have 2 completely distinct ways to map a keyboard mathematically. You can use the physical exponential formula to find the exact vibration speed of any single key, or you can use the logarithmic formula to measure the exact distance between any 2 notes. Layering algebra and logarithms over physical keys reveals the strict mathematical architecture hiding inside our instruments. Grab a calculator, pull up these formulas, and see if you can calculate the hidden math inside your favorite chords.